Yeah, this is question 10, the one that you were struggling with, so hopefully this can help. So let's just read the question carefully first. The infrared spectrum and the proton and NMR spectrum given below, and you've got a molecular formula there, C6H14O. So I think the first thing to do is just dwell on that molecular formula, C6H14O. And first thing you should always do really is see how many double bonds or rings there are in there. So if it was an alkane, i.e. no double bonds, straight chain alkane, no double bonds, no rings, you know the formula to be CnH2n plus 2. And in this case, Rn is 6, in which case 2 times 6 is 12 plus 2 is 14. So we know that it's C6H14 and therefore no double bonds, right? So from that we can get no double bonds or rings, which may or may not make it easier to get the displayed formula of that molecule. But at least we know this. And we also see that there's an oxygen in the formula, so and one oxygen, so it can't be carboxylic acid, and if there's no double bonds there, it can't be an aldehyde, but it could be an alcohol, it could be an ether. Okay, so we've done that thinking so far. Now we're going to have a look at the infrared spectrum to check out whether it's the alcohol or the ether, or in fact something else if we've missed something. And so let's have, we're not going to bother looking at this one because we know there's no nitrogen there, but we could have a look at this one, and in fact it's for an alcohol anyway. So we look at the wave number 3230 to 3550, and you know that, I think you know already from class that this is for alcohols give you quite a broad peak, and let's have a look at this peak here. It's broad, and if we have a look very roughly, you've got about 3,200 here, and you're going up to about 3,600 there. Very roughly you can see that we've got an OH bond of an alcohol in our molecule, so that probably settles it, and we could go on assuming it's an alcohol. You could go through some of the other bonds if you were doing well for time. You could go through some of the other bonds, and you'd expect to find this. Let's just have a quick look while we're at it. 1002. Yeah, look, you've got your carbon oxygen bond there. But we're pretty sure that's an alcohol now. So now that's all you're going to get from the infrared spectrum. Now you have to have a look at the proton NMR. So here's the proton NMR, and the first thing we want to do, and there's a bunch of steps that you can follow in each of these types of questions. The first of which is to have a look at the integral numbers. That's these 1.6, 0.4, 1.2, 2.4, and you probably know from class that they're the area under the curve, which gives you the number of protons we're talking about. That's why it's called integral number, because integration gives you the area under a curve, doesn't it? So you can't get 0.4 of a proton. There must be at least one proton. So just like you do in empirical formulas in GCSE and AS, we're going to turn these into whole numbers by dividing each one by the smallest number. So 1.6 divided by 0.4 is going to come out at 4. All right, so let's just change that to a 4. 0.4 over 0.4, that's going to go to 1. 1.2 over 4 over 0.4 is going to come out at 3. And 2.4 over 0.4 is going to come out at 6. So now we know the number of protons that are represented by each of these 4 peaks. So now that we know that, let's do step number 2, and step number 2 can come first, it doesn't matter. So we notice that we've got 4 peaks. Yeah, we've got 4 peaks, and that says to us that we've got 4 different environments. For our hydrogen, for our protons. So there we are, and now we're going to go through it peak by peak. So let's take the easy one first. So integral 1, that's this one here. Integral 1, let's just write it down, because you'll have to, integral 1, you'll have to write something to get all the workings marks. Integral 1, you can see there's just one proton, and it is a singlet. All right, so you can see that there's one peak there. So let me just write this down for you. So this one here is a singlet, and that means one peak minus 1. You remember your n+1 rule from class, is going to mean 0 adjacent protons, or nearby protons, or neighbouring protons. I like to call them neighbouring protons, so I'm going to say 0 NPs, and it's just one hydrogen. So in an alcohol, how do we get a single proton with no neighbouring protons on any carbons? Well, then that says to you it must be the part of the molecule that is in the hydroxyl group. So it's going to look like this. You've got your oxygen, you've got your hydrogen, and of course that needs to be bonded to a carbon. So that is the proton we're talking about in integral 1. And so let me just write that down there. And you might want to write some words, say no neighbouring protons, something like that, and one proton with no neighbouring protons. Okay, so that's the first easy one. The second easy one is the other singlet, right, which is called integral 3. Okay, so just to be clear, we're doing this one now. So integral 3. So that means we've got a CH3 group. Yeah, CH3 group, because we know from the integral number that we've got 3 hydrogens in it. And how many neighbouring protons has it got? So let's write it up here as well. CH3, comma, it's a singlet, so again, no neighbouring protons, so 0 neighbouring protons. So there we have that. Let's not draw that on the molecule just yet. I mean, I've got a pretty good idea that it's going to go on the end here, this carbon that we've drawn down in the bottom right. And that would mean that that same carbon that's on its own at the moment would need other carbons attached to it. So once you've done a few of these, you get that intuition, but you can't say that for sure just now. So let's just go through the process and look at the others. Okay, so let's do integral 4 next. So integral 4, this one here, how do you get 4 protons all in the same environment? Well, you must have 2 CH2 groups, and they're not necessarily joined together. They could be joined in separate molecules because they have to be, given their chemical shift is the same as each other, then they have to be the same distance away from the oxygen. And while we're at it, so that's where our 4 hydrogens are going to come from. And the other thing we can gather is that it is a quartet. So 4 take 1 is 3. So we're going to have 3 neighbouring protons. 3 neighbouring protons. So let's write that down. CH2, CH2 with 3 neighbouring protons each, probably. And okay, so we've got that. Now I'm starting to think that this is going to be the CH3 from integral 3. That's our 3 protons from integral 3 and it's connected to a carbon. And if that's true, then you're going to need another carbon here, another carbon here, so that these 3 hydrogens, let's just draw a little green ring around these hydrogens. So they're now connected to, they've got no neighbouring hydrogens, which is what we want. And so that's this green one here. Okay, now we have to account for the other carbons. So we're not going to write these two. Let's do these two in blue. Right, we're not going to account for these 2 yet. Let's have a quick look at integral 6 first. So integral 6. Okay, so integral 6 means we've got 6 protons, and so that's going to be made up of 2 CH3 groups. And let's count the little peaks. So this is 1, 2, 3. So we've got 3 peaks. Take 1 is 2 neighbouring protons. So now let's have a look at integrals 4 and 6. Let me change colour, which looks like black. Okay, so we're going to have a look at these. So you're looking at these 2 here, and you're going to see CH3 groups with 2 neighbouring protons and CH2 groups with 3 neighbouring protons. So doesn't that suggest that we've got CH2, CH3 twice? CH2, CH3. That suggests you've got 2 CH2, CH3 groups. It's a bit intuitive. It's difficult for me to say definitively how you get there, but you need to look at the CH2 groups with the 3 neighbouring protons. You need to look at the 2 CH3 groups with the 2 neighbouring protons, and then into your head needs to pop this result. And that comes with practice, so we should do a few of these questions. So if so, then what that means for our molecule down the bottom is we've got this then becomes CH2, CH3. This becomes CH2, CH3. Now we've sort of gone ahead and drawn all our molecule now, but what we should do is we should check that everything makes sense. Okay, so let's check go back to green and check those. All right, so these ones here, let's put these in green. This was our CH3 0 neighbouring protons peak. Yeah, so it's an integral 3, so 3 protons, and they've got 0 neighbouring protons, so that makes sense. I'm going to put a little tick by that. Then we've got, let's do the easy one. Let's make that, what colour should we make it? Let's make it grey. Okay, so we'll do this easy one. This grey one here is a single proton with, so it needs to be an integral number 1, and it needs to be have no neighbouring protons, which is very consistent with this peak here. Okay, then we've got these carbons here, these hydrogens rather, these protons. Let's change colour. Let's do purple. So we've got these 2 and these 2. Okay, they're in a different environment, and those 4 protons are these 4 here. All right, so there's an integral number of 4, so that makes sense, and it's a each one is a quartet, which means 3 neighbouring protons, and as you can see, they're adjacent to 3 neighbouring protons here and here. So lastly, what colour have we got? We've got light blue. Light blue, so we need to take account of these hydrogens and those hydrogens. So we've got 6 hydrogens altogether, and they are each adjacent to two other hydrogens there, like that. And so those 6 hydrogens are consistent with this peak here. That's that. Now, I'm not sure if you've done this in class, but looking in the textbook, it doesn't go into very much detail about chemical shift. So you can sort of pause now and leave it there if you like. Or you can listen to a little bit more detail about chemical shift. So this is, of course, is our chemical shift, this axis here. And what's happening here is you're getting less shielding as you go along the axis from 0 to 1, 2, 3, and 4. So, you know, a pure proton, right, would be way over that end of the scale, and your silane is your reference at 0. And so silane, the protons in silane are very shielded from the magnetic field that you apply to them. And then as your protons get less shielded, then that's what accounts for the peaks being further and further left. So, and I don't see that in the textbook. I don't see anything about shielding in the textbook. So if you want to understand more, we can do that in class. But it's relevant here because you've got this electronegative oxygen, and what the oxygen does is it draws the electrons towards itself, of course, because it's electronegative, and by doing so, it reduces the amount of shielding. And so that's why these, yeah, what colour can I use? Let's go to black. These hydrogens here, all right, which are closer to the oxygen than these hydrogens here, all right, that's why they have a higher chemical shift. The CH2 groups have a higher chemical shift than the two CH3 groups. There you have it. We probably need to do more detail in class, but hopefully that's taken you a step forward.